Any idea what is internal resistance? Smaller? Small r. Okay. Inside what? Inside the resistor. Then what is all these things? Outside. So suppose if I have a battery, right? So if I check the voltage across this, showing me 1.6 volt, right? So now I'm actually connecting it in a circuit, right? So now if I check the voltage across the same battery, right, voltmeter, showing me 1.48 something, right? So what happened to the, why this difference? So when I did this, right, in this circuit, right, when you are connecting only the battery, right, so there is no current flow because there is no circuit at all, right? You are just checking only the voltage difference. So there is no current flow. Whereas here there is a current flow. Okay, so that's the main difference you should understand. So here no current flow. Here there is a current flow. Okay. So this 1.6, right, is called the EMF of the battery. Electromagnetic force EMF. Even though they named it as electromotive force, right, not magnetic, electromotive force, right? It's not force, it is actually measured in voltage, 1.6 volt. So it's actually a misnomer. What do you mean by a misnomer? Wrongly named. So somebody named it wrongly, so we're still using it, right? Just like the current convention. So it's not a force, right? Electromotive force. Force means Newton, right? But then it's actually voltage. Generally, we still use the same name, electromotive force, EMF. So EMF of the battery is 1.6 volt. But when you connect it in the circuit, you got it as 1.48 volt. To make it easy, I'm going to take it as 1.5 volt. So I'm rounding it off to 1.5. This is called terminal voltage. So this is V. Voltage. So again, we are talking about internal resistance. Okay. So this loss, right, 1.6 minus 1.5, that is 0.1 volt. That is what is called lost volts. Or another name for this is back EMF. Because you lost this volt, right? It's called lost volts. Back EMF. Inside the battery, right? So the current is actually flowing in the outside circuit, but it is also flowing inside the battery, right? Only then it will be a complete circuit. So when it is passing through the battery, right, it has to flow through the, what does it have to flow through? Battery, what do you have? There is no wire in the battery. Chemicals, right? So it has to flow through the electrolyte. That resistance is what is called internal resistance. So take it down. So resistance offered by the cell when it flows through its electrolyte is called internal resistance. So generally speaking, we represent it as something like this. So just near to the battery, if I show a small resistance, right, it is actually internal resistance, right? So instead of, even though the resistance is inside the battery, right, just for showing it in the diagram, we show it as just near to the battery. Okay? So we represent it as R, internal resistance R. This is the example which I showed you here, so I think this will make more sense. 1.6 versus 1.5, so the difference is here plus 4. But here, where did that voltage get lost? Because it has to flow through this internal resistance, right? So this we are talking about in terms of voltage. So V is equal to IR, right? So the voltage lost in the battery will be I into R. So it's called as V lost. That means I'm going to say E minus IR is my V. So E is my EMF of battery again, right? This is terminal voltage. What do you mean by terminal voltage? In this case, 1.5 volt. Why? Because when it is connected in the circuit, what is the voltage across the battery? That is your terminal voltage. Terminal means between the two terminals. And this is the current, and this is the internal resistance. So even though I have written it differently here, right? So the EMF here was 1.6, the terminal voltage was 1.5, the last volt was 0.1. So I just brought it the other way around since we did the experiment in a different way. Any doubts in this? So the moment I say internal resistance, you should remember this. Okay, this is a 1.6 volt battery. But the moment I connect it in the lamp circuit, it becomes 1.5. So where did that go? That is lost in the resistance. But when I put it directly in the voltmeter, there is no current flow because there is no external circuit, which means there is no current flow through this resistor. So I is 0, so the last volt is also 0. That's why it's showing the complete voltage. Following this? So EMF means the full capacity of the battery. However, this is a little bit complicated topic. The reason for that is as the current changes, right? The current is determined by the external resistance, right? So suppose if I redraw this diagram. So there is a small resistor R, EMF of the battery. So I am having a external resistance R. And this determines the current I. So if this resistance is very high, current will be very low. So if R is high, I will be low. Okay. If I is low, what happens to this one? This value is low. So this entire value will be low. So IR, okay. Sometimes I use capital I, sometimes I use small I, so it doesn't matter. Maybe I can use small I. So IR is also small. So this value is small, right? What happens to this value? This is subtracting, right? So this value is very small. This V will be increasing. So V will be high. So V will be high closer to EMF. See if you are following this. So as R increases, I decreases. As I decreases, this term decreases. So this value is decreasing means this value will be increasing. Right? Following? So of course the opposite is also true. So when I don't connect it in a circuit, right, this terminal and this terminal are not connected. So when they are not connected, right, there is only YAR, right. So if I take a battery here, this and this, are they connected? No, but there is YAR in between, right. So YAR is the insulator or conductor? As a conductor, it's an insulator, right? Which means we can say the resistance is very, very high. So in this situation, even though there is no circuit, right, I can imagine that there is YAR connected here, right? The resistance is very, very high. And the resistance is very, very high. What happens to the current? Current will be very, very low or almost zero. So that's why if this is zero, E is equal to the voltage which you are measuring. Following this? The opposite is also true. So if R is very low, what will happen? I will increase. IR will also increase. V will decrease. So if you understand the entire material here in this one board, you can understand internal resistance. So suppose if I take the battery, right? If I'm connecting it like this. So I have connected this on the plus. If I keep it here, what do you think will happen? Battery will get heated. Why? So let's assume that this wire does not have any resistance at all because there is no carbon resistor or anything, right? Wire will have little bit of resistance, but compared to a bulb or this thing, it's directly getting connected. So if I keep it like this, right, very soon you will see that the battery is getting hot. You can feel it now itself in few seconds. Why? So R is very, very low, right? So when R is very, very low, I is very, very high, which means this value will be very high. So if I connect it like this and if I put the voltmeter, probably it's going to show me very low value, right? Only thing is on the plus side, I can put it like this. On the minus, I don't have anything to put. So you folks can, yeah, it's not very safe to do it like this, but we can try it quickly. Just touch it and see. You see it? It's getting pretty hot. So look at this. When this is the situation, right? There is no resistor at all, right? Which means the current flow is very, very high. So if I check the voltage now, what is the voltage? 0.44. You see what happened? So the I has increased a lot. So the terminal voltage has come down significantly. Are you following this? So what I showed you is two different extreme conditions. The first one is there is no current flow at all, which means this is equal to this. The second condition, it is the worst case scenario where the current flow is very, very high, which means this value is very, very high. So this value becomes very, very low. Following it, right? So why do you think it's getting hot? Because of the internal resistance. Because the current is flowing through it, and I into R is providing the heat. Right? Just when we talked about it. So I squared RT, right? As I keep flowing it for a longer time, I squared RT is going to be the heat energy.